Okay, guys, so this is an activity designed to experience and explore rate of change in a linear relationship. We should be clear that a rate of change in a linear relationship is always constant. So what makes a linear relationship linear, okay, so that word right there, linear, that defines a kind of situation that has a constant rate of change. So as long as it's constant, which means you're always adding some amount every single time. Okay, whenever you go from one thing to the next, you're always like adding the same amount every single time. Sometimes what you end up doing is you end up adding a negative amount every single time, but you're still adding. And adding a negative looks like subtraction. But it's constant, it's always the same. So in class, just to help you out with the homework, let's go over the notes that we did in class. We have a situation here where the cat is some situation regarding a cat and his distance from the bowl. So in this situation, we had the distance a cat is from his bowl through time. So that's something we have to make sure we understand. When it's the distance from a bowl, that means when there's no distance away from the bowl, that means he's next to the cat. So if we draw the little bowl here of milk, when the cat, meow, is right here next to the bowl, that is no distance. Then if we had the cat in the bowl, and the cat's over here, then we actually have some sort of distance. But if there's no distance, that means that the cat is right there next to or at the bowl. So being clear on that, let's now work through these situations. We have a situation where the cat is starting at the bowl. Okay, so starts at the bowl. And then up here, 4 seconds later, so that's the seconds. 4 seconds later, he's 12 feet. That's the distance. He's 12 feet away. So, what situation says this? He was 12 feet away from the milk. Nope, he was right at the milk, so that can't be the situation. He was 4 feet away. Nope, he was right at the milk. He was no feet away. Down here also says 12 feet, which can't be true. So we're left with either C or D. The cat ran away at 3 feet per second. The cat ran away at 4 feet per second. Well, let's see. If he's 3 feet per second, we know that he ran for 4 seconds, so 3 times 4 gives us 12. If he ran for 4 seconds at 4 feet per second, he'd be at 16. The one that matches the graph is C. So based on that being 4 seconds and 12 feet away, the C is the choice that fits this story. Or excuse me, the C is the story that fits this graph. So writing everything that we can say about a situation, well, that's saying write everything that we can say about the cat and the distance he is from the milk during this time. Well, the time it's talking about is from 0 time to this point right here, which is 4 seconds. So what happens in between this amount of time, between 0 and 4 seconds? There's several things that we could say. We could say that he starts at the bowl. After 1 second, he's 3 feet away. We can say after 2 seconds, he's 6 feet. After 3 seconds, he's 9 feet away. We could even say at a half second, he's 1.5 feet away, which would be 1 foot and 6 inches. So there's a lot that we can say that's happening in between the start and the 4-second mark. And this idea here is that there is always more that we can pull out of a graph than what's explicitly stated or clear. Like there's more than just at 4 seconds he's 12 feet. There's more than at no seconds he's no feet away. So if we have to create a table that tells the story, we saw that the x-axis, this was your time, and your y-axis, that was your distance. So because of that, your first table is always your x value. Your second table is your dependent or y value. So that means that this must be my seconds. and this right here must be my feet away. So the story of the graph starts at 0 and it ended at 4. So we're going to tell that story, 0, 1, 2, 3, ending at 4. We know that it was 0 when it started and that it was 12 feet away at 4 seconds. And based on the rate of change that we figured out, he'd be going 3 every single second, 3 feet per second. So that would be the table. I do it by looking at the graph and seeing the information there. Is it a proportional relationship? We know that the graph had a straight line between its x and its y axis, so it's definitely linear. It's definitely linear, but is it proportional? And the answer to this is yes. It's proportional because it's a linear relationship, which means straight, and it has no initial value, which means it's passing through the origin. Because it started at 0, our graph went right through the origin. And that's a graphical indicator of a proportionality. So yes, it's a linear relationship with no initial value, which is to say that the graph is straight and it passes through the origin. The unit rate for this story was 3 feet per second. Okay? It's a unit rate because it's only it's per 1 second. And that's what makes it a unit rate. So we had all those situations, A, B, C, D, and E. C was the one that was the winner, but we're going to graph the other 4. So let's look. Graph A. The cat was 12 feet away. So that means when we start, we are starting up here at 12. And then he runs towards the bowl. Well, right here, this 0, that's the bowl. These are feet away from it. So we're trying to figure out if he's at the bowl after 4 seconds, that means he's right there at 4 seconds. So in order for this to be a linear relationship, he's moving at a constant rate. He must be getting closer, 3 feet closer every single second. And so there would be our graph. The rate of change, well, let's see. I am moving over 1x, and in this case I have to drop down 3. So I'm going to use a negative sign because I'm dropping down. So that means my rate of change in this case, here's a cleaned up version of the graph, and the rate of change would be -3 because when I move 1x over, I have to drop down -3. I'm losing 3. I'm getting closer. My distance is decreasing. That's what the negative sign means. In this case, the negative sign, okay, that negative sign is indicating a decrease in the distance, or in the distance away. Let's look at situation B. The cat starts 4 feet away, which means when no time has passed, right here, when no time has passed, he's at 4 feet from it. And he runs towards the bowl, and again, on this axis, that 0 point indicates the actual position of the bowl. And at 12 seconds, right here, he hits that bowl. Well, the straight line means that he must be going 1 foot every 3 seconds. 3 seconds, he drops a foot. 3 seconds, he drops a foot. 3 seconds, he drops a foot. So that is the graph in this case. He's moving at this rate. He goes 1 foot closer every 3 seconds. Which means if we need to figure out what he goes in 1 second, -1 divided by 3 means he is losing 1/3 of a foot every single second. So this little piece right in there, that piece is actually negative, or is a dropping of 1/3 of a foot. So that's our rate of change, -1/3. So for situation D, the cat ran away from the milk. This means that he started at milk. So he's starting at the milk, and since we know that this 0 position is the position of the milk or the bowl, he's starting right there. And then he travels 4 feet per second. So 1 second over, and he went 4 feet away. 1 second over, and he went 4 feet away. 1 second over, and he's 4 feet away. So that's how I would graph this situation. And the rate of change, when I move 1 over on the graph, I had to rise up 4. So my rate of change in this case is 4. And then this last situation here, the cat starts 12 feet away. So we're going to start here on the graph, and then he moves it at 4 feet per second. So I'm going to go 1 over, 1, 2, 3. I'm off the graph, but that's where it should be, right there at 16. So the graph would look like this. And the rate of change is the same, 4. Okay, so let's go back here. I jumped ahead accidentally. So here's a question 7. We have a situation where we got to look at the story and compare it to the graph. We have the situation right here where baby is 9 feet from the edge and he's crawling towards it for 6 seconds. But then he gets picked up and he never reaches the edge. Well, if I'm looking at a graph, that bottom part is the edge. When you're 0 feet from the edge, you are at the edge. So he's starting at the edge here. Can't be the case. Here he is 9 feet from it. He never gets it. After 6 seconds, he is stopped. This is the graph that models the story. Let's look at this situation. The graph and the table describe a runner's distance from the finish line in the last seconds of a race. Which equation matches the table and the graph? Well, let's start here. He starts, when we start this countdown, he's 42 seconds from it. And that's where this point is right here. In 6 seconds, he goes 42 feet. Which means in 1 second, he must be traveling, 42 divided by 6, he must be traveling 7 feet closer, so I'm going to use the negative to indicate the closer to the finish line, per second. And we see that over here too. Okay, we see that -7 rate of change. So since this is our rate of change, and this right here is our initial value, let's see where we see that. Here we're gaining 7, but we're losing 7. So C turns out to be the equation that matches it. It has that initial value of 42, and it's got that -7 rate of change. Here we have to create a table for this graph. Well, based on this, that means when my time is 0, because the first number is time, the second number is my y-axis, or my distance. So we start at 5. And then at 3 seconds, we are 23 feet away. So let's figure out the in-between stuff. All right, my eraser is not working here, sorry. So we've got 0, 1, 2, 3. We are starting at 5. We end at 23. We have traveled 3 seconds. So we have this distance here of 3. But we did not go 23. Even though it says 23, that's not what we went. Because we started at 5, we went to 23. The gap between these two is 18. So we actually went 18 feet in 3 seconds. And 18 divided by 3 is 6. So that means we're going to add 6 to make it 11, add 6 to make it 17, add 6 to get to 23. So we have our rate of change of 6 and our initial value of 5. So if I have to tell the story of this, maybe I can say the dog starts 5 feet away, okay, because that's what I'm saying right here, and then 6 feet per second to go. So the equation, we're starting at 5. So right here, start at 5. We travel 6 feet per second. So our equation would be right there. All right. Good luck on the homework, and I'll see you in class.